Thanks for the introduction. And yes, John and I will be talking about computational complexity of converting non-stochastic Hamiltonian to a stochastic Hamiltonian. So here, there would be a Q in front, inside, in all of these are Q, there's no CH. So I try to emphasize that a little bit, but it may go down. In the first part, I will talk about my joint work with Daniel Lidar and Itai Han. And let me start with the definition. We call a local Hamiltonian a stochastic with respect to a basis if all the local terms have only non-positive off-diagonal elements in that basis. So not only off-diagonal elements are real, but they're also non-positive. Sometimes these matrices are solved with this property are also called Z matrices. Many interesting quantum models are stochastic, for example, in the natural basis that we use them. For example, transverse field IZ model, Bose-Hubbard model, particle in a position-based potential, and any classical Hamiltonian, such as classical IZ model. And because of this restriction on the form of the Hamiltonian, they enjoy some maybe nice restrictions on some of their properties. For example, the ground state of a stochastic Hamiltonian only has a non-negative amplitude. Also, if you look at a partition function decomposition of these Hamiltonians, you can write them as a sum of non-negative weights. And what do I mean by that? And sometimes we refer to this by saying that they don't suffer from the sign problem. What do I mean by that? It's the standard trick that you can write the partition function, split the exponential in L, let's say, pieces, introduce some complete set of bases in between, and write the partition function as a sum of weighted paths. And this special property that they don't have non-positive off-diagonal elements means that these weights would be positive. So one can use path integral quantum Monte Carlo to sample, let's say, to do importance sampling to sample from thermal averages. So this was from a more practical point of view, but from a computational complexity point of view, similar to the way that we can define complexity class QMA and show that the problem of estimating ground state energy of a local Hamiltonian is complete for this complexity class, one can define a complexity class STOCHMA. This is done by Bravi, DiVincenzo, Oliveira, and Terhal. And basically, one can show that the same problem, estimating the ground state energy of stochastic Hamiltonians, is a complete problem for this complexity class. Also, they show that this complexity class is expected to be strictly contained in QMA. More technically, they show that STOCHMA is included in AM, and even more restricted version of that. But the message that I want to clearly say is that it looks like for this specific problem, which is this problem of estimating the ground state energy, this complexity class STOCHMA shows up something between classical Hamiltonians and most general local Hamiltonians. And another way to emphasize this is just referring to this paper by Toby Cubitt and Ashley Montanaro, that this STOCHMA class appears as an essential part of complexity classification of local Hamiltonians, local qubit Hamiltonians. Okay. But there's some arbitrariness in the definition. So there's this basis dependent. And of course, if I rotate a Hamiltonian, eigenvalues doesn't change, thermal averages doesn't change. And what can I do with this? Let's look at the extreme case. I can always diagonalize any Hamiltonian. And of course, when it's diagonal, there's no off-diagonal element, so it satisfies the definition for a stochastic Hamiltonian. But finding this, or finding the unitary that does this, and that takes exponential time. And also, this new basis will be highly non-local. But let's look at the extreme other case, which is the simplest case. For example, if I give you the transverse field Ising model like this, so here x and z's are Pauli operators, and I give it to you with this plus sign, so I say that this plus is plus xi. You can easily see that it has some positive off-diagonal element, but you just assert it and say, oh, I can just conjugate this Hamiltonian with tensor of z's, and all of a sudden this plus sign will flip to minus sign. So it converts a seemingly non-stochastic Hamiltonian to a stochastic Hamiltonian. You can do another example. I will use this hx later, so I define it as a weighted sum of two-body x interactions. J's can be plus or minus. And of course, this is stochastic because you can have plus 1 here, and you can see that it has positive off-diagonal elements. But you can trivially, again, see that you can rotate this Hamiltonian and bring it into this form by just conjugating with Hadamard. Sorry, I used W for Hadamard just because I reserved H for Hamiltonians. And this is clearly diagonal and it's stochastic. Okay, so the question is how we can extend this. And let me just mention that there's also another freedom in the definition, which is how you define these local terms, how you group them and call them a local term, because, of course, adding to non-stochastic Hamiltonian can be a stochastic again. But I won't talk about this. We have some discussion about this in the paper, but let's focus on the first one. I hope till now I have motivated a new definition, which is let's allow some polynomial time classical pre-processing on the representation of the Hamiltonian that you are given, and to try to make it a stochastic. To be a little bit more formal, so we say a family of local Hamiltonians represented in a given basis is computationally stochastic. If there exists some polynomial time, some efficient classical algorithm, such that for any member of this family, the algorithm can give me both the unitary and also the rotated Hamiltonian with the property that this new Hamiltonian is both local and stochastic. Of course, one can extend the definition beyond unitaries. The example that I gave earlier, Hx, considered previously, is computationally stochastic because, as I said, we can conjugate it with Hadamard, write it in eigenstates of X operator. It's trivially stochastic. And also, we don't expect general local Hamiltonians to be computationally stochastic because, as I mentioned, we don't expect QMA to be equal to a stoch QMA. Before going to the main result, let me just highlight 2 points. So with this definition, and by the way, here I say curing, and by curing I mean converting a Hamiltonian into a stochastic form. So with this definition, we don't care about the running time of quantum Monte Carlo on the new Hamiltonian. So here, the cured Hamiltonian is some Ising model, which can still be NP-complete to approximate the ground state. But we say that this transformation is efficient to just bring it into this form. And the other thing that I want to emphasize is that the computational problem that we consider here is finding this curing because we want a transform system which preserves all the thermal averages, or let's say in this specific choice, eigenvalues of the problem. And this is in contrast to other approaches that compare hardness of a quantum Monte Carlo simulation of the fermionic and bosonic version of the same Hamiltonian. Okay, so main result. So we look at the simplest Curing transformation, simplest choice of operators that I can think of. Just tensor of local operators. And I ask, someone gives me some Hamiltonian, and I just want to know, is it possible to find a unitary in this form to make the given Hamiltonian and bring it into a stochastic form? It's straightforward to show that if UIs are Paulis, I mean, this decision problem is efficiently solvable because you can just expand the Hamiltonian, let's say each of the local terms in Pauli basis, and conjugating a Pauli with Paulis only change a sign. You can just write down some linear set of equations and find the right conjugation, which can be done efficiently because it's basically a linear system of equations. It's not linear equations. But what about if we go beyond Paulis? And I go one step further. If UI belongs to the single qubit Clifford group, then this problem becomes NP-complete for 3 local Hamiltonians. And then, okay, this group is discrete. Maybe this is some artificial fact. Maybe if I allow for some continuous rotations, which is more natural in this setting, it's easy to solve this problem. But then we also show that if UI belongs to single qubit orthogonal group, then again, this problem is NP-complete for 6 local Hamiltonians. So basically, let me emphasize that here we are saying that for the simplest choice of rotations, just tensor of local operators in these forms, even for this simple case, this problem of converting a Hamiltonian into a stochastic form is NP-complete. Okay, before I will talk about the proof in one slide, but before that, let me talk about implications. Okay, this I already mentioned, that even for trivial choices, this is already hard, but let me rephrase the problem or talk about another problem, which is I start from some stochastic Hamiltonian, and for each qubit, I choose some random Clifford and rotate it with it. So the new Hamiltonian in this new basis would be non-stochastic. The bit string that defines this choice of Clifford operators would act as some key or classical bit string that maps the non-stochastic Hamiltonian into a stochastic Hamiltonian. So if I think about planted solutions, I can say that even if I have the promise that non-stochastic Hamiltonians can be cured by some trivial change of basis, finding that can be NP-complete, it's unlikely to be efficient. And also let me talk about an open question, or maybe an observation, is that basically this question that is it possible to use this mapping to generate efficiently simulable spin models that are inefficient to simulate using quantum Monte Carlo unless you have this secret key, this classical bit string. And we talk about some maybe cryptographic applications in the paper, but let me talk about the proof. So a sketch of the proof, and the proof is done by reduction to 3 SAT. Here I will talk about a very specific case, which is even choosing between identity and Hadamard can be NP-complete. And to see that it's not hard, just look at this term. It's defined in 3 qubits, I, J, K, and it only has Z operators. So I define it like this. And I ask, what combination of Hadamards should I use to convert this Hamiltonian into a non-stochastic Hamiltonian? This Hamiltonian already is diagonal, so it's trivially stochastic. And I ask, what combination of Hadamard should I apply here to get it into a non-stochastic form? You can go through all choices for variables xi, xj, xi, xj, xk, and you can see that you get this table. The only case that you get non-stochastic Hamiltonian is if you conjugate all the qubits, all the 3 qubits with Hadamard. And this is exactly the 3-sat class table for in this 3-sat class table. And then the idea is that, okay, I also construct the other clauses, just conjugating the same Hamiltonian with Hadamards, construct the other clauses, and then add all these clauses together and map any 3-sat problem to a 3-local Hamiltonian construction. By that, I can basically I can prove this lemma, which is if the choices of UI are restricted to I and, between I and Hadamard, already this decision problem is hard. And sorry, why? Anyway, I don't know why. But but how to go from these two theorems that I showed? You just add some extra terms, which I call them gadgets, and you restrict your choices in these groups to the choice of between identity and Hadamard. That's basically what I wanted to say, and we saw that even simplest transformations is already NP hard, but what about special cases? And that's exactly what Joel will talk about.
Oh, this is back. This is forward. Okay. Hi, my name is Joel. I'm a postdoc at QTech, and I'm working with Barbara Terral on this project. I want to thank the organizers of QIP for inviting me, and I want to thank Milad for his excellent talk and for doing a lot of the footwork for me, so I get to talk about more of my project. So Milad has discussed that in general it can be hard to decide if a Hamiltonian is computationally stochastic. But that doesn't mean we can't try. So Barbara and I have been working on identifying Hamiltonians for which it is feasible to decide whether or not whether or not a Hamiltonian is stochastic in some local basis. And I will present a constructive polynomial time algorithm for deciding if a generalized Heisenberg XYZ model is stochastic in some local basis. And here by local basis, I mean a basis which is similar to the computational basis under local unitary transformations, so one local unitary transformations. Whoops. So the general problem statement we're interested in is to know if you give me a 2-local Hamiltonian on n qubits, can I tell you whether it's stochastic in some local basis, and what is that basis? And there's been lots of work in the quantum Monte Carlo community on avoiding the sign problem, but there have been very few systematic approaches in this stochastic picture. Many of the approaches that have been proposed offer sort of limited strategies within particular regimes of certain Hamiltonians. And what we'd like to do is try something more general. I don't know if you want me to stay on this for too long, but I'm going to just continue. So here what we're going to consider is a generalized XYZ Heisenberg Hamiltonian on n qubits. So what I mean by that is we have a Hamiltonian broken up into 2 local terms, and the 2 local terms contain XX, YY, and ZZ interactions, and these interactions have arbitrary independent coefficients, and the Hamiltonian lives on an arbitrary interaction graph. And our claim is that there's an efficient algorithm that runs in time O(n cubed), where n is the number of qubits, that decides whether or not this Hamiltonian is stochastic in some local basis. And the algorithm finds the local basis, or it tells you that no such basis exists. And this is where our paper is. This is the first systematic procedure for a highly generic class of Hamiltonians for deciding whether or not a Hamiltonian is stochastic in some local basis. The previous techniques have mostly just given sort of sufficient conditions under certain regimes of a Hamiltonian. So I'm going to explain the algorithm because it's kind of difficult to follow, and if you read the paper you might get lost, and so I kind of want to have this for, prosperity. So before I do, I want to establish some important facts. The first fact is that what we're going to do is we're going to treat each 2 local term as a diagonal 3x3 matrix. That is to say that we're going to introduce a new matrix called what I'm going to call the beta matrix, and I'm just going to populate it along the diagonal with the real coefficients of this Hamiltonian. And when we do this, we can make use of the isomorphism between SU2 and SO3. So if I have a SU2 transformation on my 2 local term, these are 1 local unitary operations, then this is going to translate into SO3 rotations acting on the left and the right on this beta matrix. Now, in order to be stochastic, you can sort of take my word for this. This transformed beta matrix must remain diagonal after it's been transformed in this fashion, and it must satisfy this inequality. And note here that I'm switching notation here from XYZ to 1, 2, 3. This inequality, you can sort of see why it's true. We kind of need, this YY term has alternating plus and minus signs along the diagonal, and this XX term has all positive signs. And so we need this XX term to sort of drown out the sort of highest positive term on this YY entry. And so with this construction, our Hamiltonian looks like a matrix-weighted graph. And what we're doing is we're applying SO3 rotations at the vertices, and these SO3 rotations act from the left and the right on the edges of this graph in this fashion here. Oh, I keep getting confused by that. So our algorithm finds the appropriate SO3 rotations, or else it states that no such rotations exists. And it relies on two important points. The first point is that it actually turns out to be sufficient to consider just signed permutations. And these correspond to single qubit Clifford rotations on the Hamiltonian. And this helps us discretize the problem and make it easier to solve. And you can sort of naively see why this might be true. If I'm taking a diagonal matrix and mapping it to another diagonal matrix, then you can always do this by acting with signed permutations on the left and the right. But when you have your matrices living on a graph, then this sort of becomes non-trivial, and this is something that we had to prove. The second important point I'll make use of is if my beta matrix has rank greater than 1, that is to say there's a high rank beta matrix, then the sign permutation acting on the left and the sign permutation acting on the right must be the same up to a difference in signs. And so given this, our algorithm is going to, and this is in order to preserve the diagonality of the beta matrix. So given this, our algorithm is going to break up into two parts. The first part is to determine what permutations we need to assign to the vertices so that this inequality is satisfied, and this is a necessary condition, and also so that the diagonal form is preserved. And the second part is to determine which signs we can add to these permutations so that we can satisfy this inequality. And if all these conditions are satisfied, then we'll have satisfied this inequality and we'll have preserved the diagonal form of the beta matrix. So let's proceed. So the first part is to determine which permutations to apply to the vertices. And the first thing we need to do is identify sets of vertices connected by paths which are composed of edges which have high rank beta matrices. And I'm going to call these high rank connected components. And on these high rank connected components, the permutations that need to be applied at these vertices must all be identical. And this follows from the fact that for high rank edges, the permutation acting on the left and the permutation acting on the right must be the same in order to preserve the diagonal form. And so for each of these components, we're going to check this condition. And there will be maximum 6 permutations that we'll need to check in order to see which ones satisfy this condition. And going forward, we're going to throw away any potential permutation assignments that fail this check. And now what we can do is we can sort of identify, so if we have these and these are rigid connected components, we can sort of collapse them down to a single vertex. And so we can sort of modulo out these high rank connected components. Sorry, I might have called them something different just there. And we can treat them like a single vertex. And the remaining edges are all going to be rank 1, and we can label each of these edges by the index of the non-zero diagonal entry of these rank 1 matrices. Yeah. Now, in order to satisfy this inequality on these rank 1 edges, we want to apply permutations at the vertices to remove all the 2s on the edges. And the reason this is true is because if this thing is non-zero, then this thing has to be non-zero, but this can't hold if we have an edge which only is with a matrix weight which is only rank 1. So for example, if I have a vertex in my graph and it's connected to edges labeled by 1, 2, and 3, then it's impossible to remove an edge labeled by 2, because if I apply a permutation, it will just cycle around these labels. And so in that case, we could claim that our Hamiltonian cannot be made stochastic and terminate. So going forward, we'll assume that our graph is composed of vertices whose edges have at most 2 different labels. And now what we're going to do is we're going to do a little bit of surgery, and you'll see why I do this shortly. I'm going to remove any vertices that are connected to edges labeled by a single label. And I'm going to add in some extra edges to keep track of those removed, to keep track of the fact that these vertices are still connected to an edge labeled by that number. And now what we have is a graph where every vertex is connected to an edge labeled by exactly 2 numbers. And what I'm going to try and do is get rid of all the 2's. And so there's 2 things that we need to consider. We need to consider that we need to apply permutations so that the edges to which this vertex connects their labels are mapped to something other than 2, because I need to get rid of all the 2's. And also the permutations acting on the left and the right of an edge have to agree on what they map this label to, this label I to, because they need to preserve the diagonal form of the matrix. And so, for example, if I take a vertex here and it's connected to edges labeled by 1 and 2, there are 2 possible permutations I could apply to it. But this choice is fixed by what my neighbors are, and that's applying this rule. And so what that does is it gives me a kind of rubric or instruction set for how to satisfy this problem or how to solve this problem. And I'm going to add an additional piece of information, which is that I'm going to label these permutations by a plus sign and a minus sign. That is to say, if I have a vertex connected by a 1 and a 2, one of my permutations I could apply is going to be labeled by a plus 1, and the other one by a minus 1. And now what I have is a case where if you give me a vertex and what in the edges it's connected to, and you tell me what sign you assign to it, then that will uniquely specify what permutation I have to give. And so what I've done then is translated our problem of removing the 2's on this graph into an Ising problem, and a problem of finding the exact satisfying solution to an Ising problem. Right, and you can see why that's true, because if you have an edge labeled by 2, then it requires that the numbers which are assigned to those vertices must differ. And if I have an edge labeled by a 3 or a 1, then they must be the same. And so an exact solution to this Ising problem corresponds to a valid assignment of permutations, which would remove all of these 2's. And this is easy to do, and there will either be 2 solutions or there will be no solutions. And if there are no solutions, we can claim that our Hamiltonian is not stochastic. If there are 2, we can continue. So these 2 solutions specify the permutations on these vertices, but there's an ambiguity when we put the vertices that we removed back in. And that's because if our permutations applied to these vertices, for instance, map to 3 to a 1, I know this is a little messy, but just bear with me, then whatever permutation I have to apply to this vertex in order to maintain the diagonal form must also map a 3 to a 1, and there are 2 possible permutations which do this. And so what we end up with is actually 2 families of compatible permutation assignments. And that is to say that we have 2 Ising solutions, and then there are multiple valid ways to fill in these remaining vertices. But the important point is that the numbers on these edges will all be transformed in the same way, regardless of what choice I make for the permutation at this vertex. So we're going to move forward, and we want to assign signs to all of our edges so that this inequality is satisfied. This is the second part of the algorithm. Since the edges labeled by 3 don't matter for this inequality, don't have any bearing on this inequality, we're going to remove them. And so what we're left with is a graph with these sort of partitions. And we're also going to expand these vertices back into their rigid connected components. And then for each of these partitions, we're going to fix a choice of for each of these partitions, if we were to fix a choice of permutation on one of them, then the problem of making this entry negative, again, goes down to an exact satisfying solution to an Ising problem, which is again easy. But there's a problem, and the problem is the following. The families of permutation assignments that we have may be exponentially large. And so, if we were to choose a permutation and test it, we might find that there's no satisfying solution, or there's no satisfying assignment, but we could choose a different permutation set and assign it to these vertices from our same family and find that there is a satisfying assignment. We can't check all these combinations, so how do we get around this? So the thing to note is that if we're considering an individual partition in this graph here, one of these partitions here, we don't care about what permutations we apply to some of the other partitions. And so what that means is we only care about the differences on the permutations on the vertices in that partition. And the only vertices which are going to have possible choices for permutations are those vertices which are connected to edges only labeled by a 1, and those vertices which are connected to edges only labeled by a 3. So in the case of edges labeled by 1, any permutation choice that we have is not going to change what the action of that permutation does to the edges it's connected to, because it's always going to be mapping those edges to 1. And so for the purposes of deciding this inequality, it doesn't actually matter which permutation we choose. And so we can choose one as a representative, and we can throw the others away. And so then we avoid this sort of exponential explosion in that case. For the vertices connected to a 3, they constitute their own sort of partition. That is to say, when I performed this expansion here, the vertices connected only to a 3 will be their own little partition. And as such, there will only be 2 possible choices of permutations I'll have to check on those sets of vertices, which limits the size of the things I have to check. And so we sort of avoid this exponential explosion in this way. And that's basically the algorithm. Once I've sort of bounded the number of permutations you have to check, and you can easily go through them and see which ones work. And so that's it. Either we've found some signed permutations that correspond to single qubit Clifford rotations, which make our Hamiltonian stochastic, put it into a stochastic form, or no such signed permutations exist. And it follows from a lemma that I prove in the paper that no local unitary rotations can exist either. In terms of future directions, we'd like to sort of generalize this algorithm to a generic multi-qubit 2-local Hamiltonian without any 1 local terms. We'd like to understand what happens when we add a 1 local terms, and our expectation is that this will probably make the problem quite hard. We'd like to consider generalizing something to consider constant depth circuits or other efficient transformations besides local unitary transformations. And this last point Malad talked about a bit, so I won't repeat it. Thank you.
Okay, so now we'll take questions for both speakers.
So I have one question for each speaker. So maybe, I don't know, question for Joel first. So is the reason this doesn't work for generic multi-qubit 2-local Hamiltonians because you're allowing, you don't require the unitaries at each place to be the same. You can have different ones everywhere.
Well, I haven't claimed that it's not possible, but I haven't been able to do it yet.
And but that's the blocker.
The easy part of this is the fact that these started in the diagonal form, and then preserving the diagonal form just means that they're the same on both sides.
Because I seem to remember from our classification paper that when you need the local unitaries to be the same everywhere, I think there's an efficient algorithm. But of course, that's not.
But this is not the case here.
Exactly. Yeah. Okay. Good. Yeah. Thanks. That clarifies. And then for Milad, so I guess the results show that MP hardness when you have general SU transformations, but not completeness. So do you expect the general question where you don't put any restrictions on the local formally of the group the local unitaries are taking from, do you expect that to be QMA complete or?
Here, you can use this mic.
So you mean going beyond local unitaries into
well, if I understood right, you had MP hardness, but not completeness.
Well, so for completeness, I assume that I'm given each of these local terms.
Indeed. So if you don't have, that assumption, but you just ask the general stochasticity question.
But then unitary can be very complicated and can rotate the local Hamiltonian to a very non-local.
Indeed. So would you expect? Do you anticipate you would get something like QMA completeness at that point?
It's always in NP because the prover can give you a constant depth circuit.
I guess the question is something else. So I guess he's asking what if unitaries are very complicated, and then, but then, so I don't know the answer. I don't know. So it's a good question.
But you have to define
diagonal.
Well,
Exactly.
the definition said that the original and the transformed one both had to be local.
Yes,
Indeed.
so
So that's a restriction.
exactly. So
In that case, this is NP. This is in NP. In local case, it's in NP.
No. The Hamiltonians, the first and last, the starting and ending Hamiltonians had to be local, but the unitary didn't. There.
So here, finding the unitary, so let me, I guess, to explain for everyone. Here, everything's fine because unitaries are tensor of local unitaries and tensor of local operators, and Hamiltonian is local, so the converted Hamiltonian is, again, local, and then we can check it, so it's definitely is NP. And then the question is, what if you can find some unitary that is very complicated, and then you have this local Hamiltonian, and the converted Hamiltonian can be very complicated. So do you expect that this problem, what's your expectation from the computation, for the complexity, for the hardness of this? I should say I don't know a good answer to this.
So Milad, you talk about some cryptographic applications. So for that, you need average case hardness. Do you have that as well?
No. So whatever result that one can prove for the tree set basically goes directly to this. So if, let's say, I didn't talk about it here, but for example, if you can look at, let's say, restrictions on tree set, if you look at average case for a tree set, everything goes through this. But for this cryptographic application, there's still one more important thing, which is in this last line, this construction that we have, it's not, let's say it's frustrated. So I don't know that quantum Monte Carlo would be efficient in the stochastic case. So this is the question is, for example, can you come up with a frustration-free version of this so that you can do the cryptographic scheme? So this is one step before that.
And such that the ground state is non-trivial, which is another. No.
Hi. So, is there some sense in which the sign problem can be cured approximately, and does that make the problem easier?
So the definition of the problem, the intuition that you have becomes very complicated when you want to rigorously define this. One easy way is to say, okay, if I define a Hamiltonian to be a stochastic if I allow some epsilon error in the off-diagonal elements. But it's important to know what we are interested in. At the end, we are interested in, let's say, in the simulation of a quantum Monte Carlo. It's not necessarily that giving equal weight to all these off-diagonal elements translate to the same efficiency for the quantum Monte Carlo.
Yeah,
so
it can infect your simulation.
Yeah, so I just want to say that, so we have thoughts about it, but making it rigorous itself is challenging.
So even small things can sort of become very important as you go along.
It might be for some, yeah.
Yeah. Now, it seems to me that there are some trivial cases, and you might be able to decompose this thing. For example, if you start with a stochastic Hamiltonian, then the identity matrix will turn it into a stochastic Hamiltonian.
You mean by adding the identity matrix?
Just by saying, here's the identity matrix, this is your transformation. Similarly, you can imagine trivial rotations around the x-axis or similar operators. So the question is, would there exist in general a sequence of trivial operations which would add up to the complex operations that you're talking about here?
Sorry, I didn't get the last part of the question.
Well, let's look at this. We begin by saying that there exists some Hamiltonian family such that H prime equals I, H, I, because it starts out being, stochastic. So that there clearly exist Hamiltonian families that have that property. And then we say there also exists a family of local Hamiltonians that have the property that U is a relatively trivial function. For example, it consists entirely of rotations around X, or whatever the equivalent is in your basis space. And what I'm asking is, if I have a family of U operators, such that we have U sub x, U sub y, U sub z, etc., and we then say, by putting different weights on these operators, we could then build a decomposition description of the U operator here. Now, if you're able to do that, I mean, this is a very preliminary thought I'm having, but if you're able to do that, it seems like you should be able to decompose this U matrix, U operator, in such a way as to be able to analyze it more efficiently.
So I don't see why you think you can make it more efficient by this decomposition, because if you can show that for even simplest building blocks that you are using, already this problem is NP hard, I don't see necessarily, I mean, right now, maybe I don't understand the question correctly, but when you show that it might be the case, but there's a caveat here. So it might be the case that you show the hardness for the simplest case, as we did, but for a more, let's say, broad family of unitaries, those specific family becomes easy, because now you have some more room to search for. So it might be that for those families it becomes easy, but then the question is does there exist some other family of Hamiltonian that problem is hard for it or not? And I think it should be like that. So for any restriction on the family of unitaries, for example, if you say it's constant depths, then one can probably, my conjecture is that one can construct a family of Hamiltonians with this property that it's NP hard to decide.
Okay, one more question.
So I just had a comment on the previous question. You were asking about the complexity of the approximately curing the sign problem, and we have a result on this with Dominik Hangleiter, Ingoroth, and Jens Eisert, where we show it's NP complete. Even so, we develop a measure of non-stochasticity and show that if you can improve, then you can solve NP in some sense.
So the measure is about off-diagonal elements, or the measure is about approximation of the quantum Monte Carlo?
It's in the measure of the off-diagonal elements that have the bad signs. And there's more than you can do on that.
That I understand. So that's an easy way of, exactly. So that's an easy way of characterizing this. But how this translates to the approximation that you have on the quantum Monte Carlo is another story. Yeah.
Okay, let's thank all the speakers in the section again.